This is my CNC ATC with a dockable dust boot. When I first decided to do the project, I thought it'd be fairly quick and easy given the amount of online resources that I'd have to complete the project. I read somewhere online that people attempting this either had too much time on their hands or too much money. I guess since I was retired, I fell into the first category of too much time. I can only say that that person was right, as I severely underestimated the scope of the project from start to finish. In total, it took me about 4 months. I have a GitHub page linked with all the code and a bunch of resources that I compiled while completing my upgrade. The intent of this video is to give people who are using Mach 3 and want to upgrade to CNC with an ATC an overview of the complexity and some of the obstacles or roadblocks I ran into in the project. The link to the resources will be helpful so they don't have to reinvent the wheel. First off, why do the upgrade? Besides being a cool feature, I really dislike tool changes. On one small project, I was making some plaques for friends that involved about 4 or 5 tool changes and took 3 hours. Every tool change creates a potential for something to go wrong. For example, running the wrong tool path for a particular bit, or something going wrong with setting the zero height. Both have happened more times than I care to admit. The second was wasted time. On various projects, I have tool paths that are less than a minute to over an hour. It wasn't really a productive use of time watching tool paths run. With my plaque job, the ATC took half the time because I added larger clearing bits, and the tool change macro did the tool change way faster than I could. The added bonus was no babysitting. After setting the first tool height, I hit start and walked away for the estimated machine runtime. Before I started spending big bucks on the ATC rotor, I thought I would start slowly and do upgrades that I'd need to do regardless of whether I added the ATC. This meaning adding new inductive sensors for homing the axes. I did this because I didn't think my mechanical limit switches were accurate enough. I then thought about how to add the dust boot. Something as simple as the dust boot actually caused quite a bit of work. Life is all about compromises, and so is my CNC. My CNC is a dual-use machine. It can be used as a plasma cutter or as a router. Unfortunately, the plasma cutter arm is beside the router, and this causes issue with clearances, especially when using post-type tool holders. Because I was mounting my tools along a rail, I could not use the dust boot that was fixed to the machine because the dust boot does not drop below the tool holder. This left me with the option of a dust boot actuator that could lift the dust boot out of the way while still attached to the rotor. I found this to be too complicated, so what I did was use a dust boot where the bottom half gets docked so it's out of the way during a tool change. Once that was done, I had to worry about the type of rotor to purchase, and just because I like to complicate things, I decided to go for a rotor that had inductive sensor switches to monitor the tool clamp state and a thermistor that could monitor the temperature in case the rotor got overheated. Mach 3 is a great program, but it has its limitations, so this is really where all the work came in. The more complicated the tool change, the harder it was to integrate into Mach 3. An example of this is getting a tool change to stop if there is an error, such as the clamp state being closed when it is supposed to be open. Mach 3 is just not that flexible. Even when you think you found a solution, it appears to be a dead end when you try using it. A perfect example is waiting for inputs during a tool change. Because I'm using tool forks, it's a very bad idea to try lifting the rotor out of the forks if the clamp hasn't released. I thought this would be an easy solution, as Mach 3 has a system wait for command that I thought would just wait for the Z-axis move after the clamp opened. Unfortunately, for some reason, this did not work for me. I'm not sure if it's the way I use the code or the program just didn't work as advertised. Another example was monitoring air pressure and temperature to ensure built-in safeties would stop the code if something went wrong during a job. Mach 3 could not handle these functions. This required an Arduino interface which took the input from the thermistor on the router and converted it to temperature and then triggered the relay if the temperature went out of limits. Same thing occurred with air pressure. In any case, as you may suspect, I am pleased to announce that my unintentional test on the safety system paid off when I forgot to turn the air on. These examples and a host of other little issues caused a bit of grief. I confess that I'm not a coder. I'm more like a monkey bashing on a keyboard trying to get the code to work. My superpower is stubbornness. The code may not be pretty, but it works on my machine. Another way of putting it is, sometimes the monkeys just win. As I have previously mentioned, I have set up a GitHub page. The GitHub page contains most, if not all, the files required to complete the upgrade. They include the Arduino code, screensets, brains, tool change script, STL for dust boot, and a spreadsheet with the pinout, and some other resources. The next section of the video will illustrate some of what is in the GitHub link. Input monitoring is done with Mach 3 brains. There are a number of videos which explain brains. I recommend watching a video from CNC for You UK, and the title is Introduction to Brains Mach 3. This video is a great overview of brains, how they work, and how to program them. I use 3 brains. The largest brain is the ATC brain, which is referred to in the ATC screenset input section. Basically, the ATC brain converts inputs and outputs to OEM LEDs to monitor state changes. An example is OEM trigger 2. Trigger 2 is activated when the ATC clamp is open. When this clamp opens, OEM LED 1212 will illuminate. During a tool change and prior to lifting the router after the tool release solenoid is activated, the script will look for the tool state of OEM LED 1212. If the state is correct, the tool change will continue. If not, you will get a message box. Clamp took too long to open. This message box stops the tool change. This ensures that there is no damage to the tool holder if for some reason the clamp did not open and release the tool. The limit switch brain will stop referencing if any of the limit switches are triggered. The e-stop brain has three functions. G31 code is used for both tool setting and auto tool 0 functions. This is a bit of a problem as that function requires the trigger to be the probe input on the ports and pins page. Because I have both a tool setter and a touch plate hardwired to different inputs, I need to switch the probe inputs between the two depending on whether I'm setting 0 tool height or I'm setting a tool offset. Normally the touch plate is on port 2 and pin 13. The only time I need to use the tool setter is when I need to reset or set the tool offset height. This is usually because I want to change one of my tools or because I've broken a tool. When I need to use the tool setter, I have to go into ports and pins and change the probe from the normal touch plate input to the tool setter probe input, which is port 3, pin 2. This brain prevents damage of my tool setter by monitoring the tool limit switch if there is over travel. This is usually caused by forgetting to change the pinout prior to running the tool offset program. The brain also monitors relays that are triggered through Arduino when either the pressure or temperature is out of limits. OEM trigger 1 is for the tool setter limit switch, OEM trigger 5 is for the pressure, and OEM trigger 6 is for temperature. In summary, brains can be used to monitor signal state or it can issue Mach3 commands. In the previous examples, the ATC LED brain was used for monitoring inputs and outputs and then turning those signals into LED states, which are used by Mach3 when running scripts. With the limit switch brain and the toolset e-stop brain, brain control was used to send commands to Mach3, usually stop or reset commands. Screensets are user interfaces for Mach3 control software. The standard 1024 screenset for Mach3 has 6 pages. The program run page was modified to include functions that control and monitor ATC operations without having to refer to other screen pages while running programs. In particular, the program run page was modified for controlling the air solenoids for manual tool changes and, when the programs are running, monitoring the air state. The information section was modified to add an ATC Tool 0 button and also an LED to indicate touch off. The ATC page is used for both ATC setup and diagnostics. The tool change section allows you to monitor the tool change and toggle auto tool change and tool offset modes. The ATC LED brain monitors inputs. Some inputs are connected directly to Mach3, while others are processed through the Arduino board and then linked to Mach3 through a relay board. Outputs are used for manual tool changes and monitoring. They use the same functionality and encode as on the buttons on the program run page. The current tool DRO allows the user to set the current tool. The dust dock and tool setter positions are set manually. This allows you to move either without having to modify the base code. The touch plate thickness is set here. This thickness is used by 2 button script on the program run page. The first is ATC Tool 0 and also 0 Tool 0. These are used to reference the Z height to the workpiece. The tool 0 length DRO is used to calculate the tool offset in the tool table for individual tools. In order to calculate the tool offsets in the tool table, you need to have a reference tool distance, which is tool 0 length and the length of the selected tool. When the tool offset button is selected, a G31 code, which is a probing operation, is run. The tool offset script will modify the tool 0 length DRO when the current tool is tool 0. If the current tool is greater than 0, the tool height offset for the selected tool will be modified in the tool offset table. To summarize, when using the tool offset, the distance calculated for the offset is placed in the 0 tool length DRO if the current tool is tool 0. If the current tool is from 1 to 10, the measured distance is recorded in the height cell for the tool in the tool table. This is the M6 start.m1s file that Mach3 uses for tool changes. Please do not ignore the caution, which I will now explain. The tool change has built-in safeties. It looks for the clamp state prior to moving. This is particularly important when dropping a tool off, as the rotor lifts vertically away from the tool holder. If the clamp is not open, the rotor will stop and a dialog box will appear asking if you can confirm the clamp is open. If you cannot confirm the clamp is open and you acknowledge the dialog box, the tool change will continue and the rotor will move vertically, likely damaging the tool fork if the clamp was not open. Unfortunately, Mach3 will not allow any commands, including reset or page changes, while the dialog box is open. This means the only way to safely stop the tool change is by doing a hard reset using a mechanical reset button that you should have on your Mach3 machine.